All right, started class by making an adjustment to the calendar. Did you see all that? Okay, and I put little stars by questions, by ones that I don't know. I don't. I think I'm still going to keep them on the test and maybe count them as extra credit. Um, and one is a little bit tough, and I'll show you what you can do with it real quick. But what I will not have, and what I kind of put stars on the calendar by as optional questions, are ones that deal with an equilibrance. What's the state of equilibrium, by the way? Which is not this first one that I have, number 5 drawn there. It has nothing to do with this. What's the state of equilibrium? When forces are equal but acting in opposite directions. There you go. Good. Awesome. So that's what an equilibrant is. Do not write this down. I swear to gosh, I'm going to yank that pencil right out of your hand or pen if I see you writing anything down about this. But I think what I'll post the notes on this. There it is. And again, I don't know what student. Who did I work with when we were pulling on 2 ropes? Anyone in here? Who was it? Yeah, you and I. And 1, 2, 3. Psh. Or ever hear of pumpkin chunking? Ever hear that? Yeah. Hey, so here we go. We got the rubber band. Someone pulls back on this. Right, so go. Psh, right. Here's the rubber band, and then here's the flight of the pumpkin. Right? Got it? Okay, so that's the same idea. But really, what it is we're pulling, and then the resultant. The pulling this goes this way. So what's the equilibrant? The equal opposite force, right? So it's really not that hard. An equilibrant is equal to the resultant, correct? Okay, the only thing that's semi-hard, which just requires some basics law of signs, is what is the direction of the equilibrant, like off of this 48 Newton side. And all you have to do is go through a process of solving, and then after you get a couple other pieces of information, you just do some basic trig there. I'm just going to leave it at that and go to ones that we're actually going to do. Okay, so optional. Incline we're going to come to in the navigation problems. But this is just the same old, where you might want to write this down if you're a note taker. And then I'm going to bother you. By the way, you're in cat. Meow. You don't do what? You do what? You don't do nothing. You do something. Whoa. That almost. Would you have sued? All right. So again, somebody's pulling this way. Somebody's pulling that way. Ready, set, go. Pumpkin chunking. There's where the pumpkin flies. Okay, I don't know how else to explain this, how you understand how this is what occurs. So the true drawing of the diagonal is the completion of the parallelogram, flashing these forces across, because parallelograms, the sides are equal. And then that's if you read the question, which I told you to read or gave you some time offline. That's one of the things we have to find. And then just for purposes of variables, the other thing is we have to find the resultant. So we have to find x and or y. Okay, and then I shouldn't even have to cover this. I really shouldn't. Because what's this angle measure? How can I simply find it? Okay, 7850 minus 4110. Very simple. What's 50 minus 10? 40 minutes. So I don't have to do any borrowing for the minutes. All right, and then what's 78 minus 41? I don't know. We'll figure that out offline. Okay, that took 10 minutes. No, I'm just kidding. All right. What's this angle measure? Fumble. We get a fumble in class. Same guy. Man, he fumbles like slamming his Chromebook. All right. How do I find this angle measure? Fumble. Now it's a fun game. We got to take 180 minus this, right? Now, what he said, or let's do the opposite. Like, how many minutes do I need? 50 minutes? How many more minutes do I need to make a degree? This is what I did the other hour. 10. So I know I have 10 minutes. Okay, what's 10 minutes plus 50 minutes? 60 minutes, and 60 minutes represents a degree. So this might be simple. Now, how many more degrees do I need to add to 78? Like what do I have to add? 101 or 102? It's one of those two. It's 101 because I need to be a degree short. 101 plus 78 is 179, and then this represents the 60 minutes. That's the leftover degree. Okay, and then okay, and then I think actually I have everything that I need because I could cancel. Well, not really. What's this angle measure right here then? 41 what? There's two reasons. The simplest reason is these are alternate interior angles. The other class, we flashed them across. We alternate interior this one. We found every angle in every spot. Now, I swear to dog, everyone in this class should be able to do this now. It's very simple. How do I find x? What angle is opposite x, everybody? Come on, say it. So what do I do? Sine what? 4110 over what? Equals what's given that works to help us solve this. Sine what? 3740. Why? Because what's opposite 3740? Okay, now, how do I do 40 minutes? What do I do when I type that in? You add 37 plus 40 over 60. Start working on that. How do I find y now? Because that's ready. How do I find y?
Sine 3740.
Sine 3740 over 176 given equals what? So just because of what's given, this that's a degree. This is ready for law of sines, or law of sines makes us ready. I'm waiting for these answers. We're not doing anything else until I get a whole bunch of students get these answers. All right, we got our two answers. I'm not covering how to plug that in. We talked about sine 37 plus 40 over 60, so you don't have to worry about finding that minute button, and you can do it on any calculator. All right, and then same old, same old. I did something silly, and we left a lot of awkwardness in the last hour. You comfortable over there? Okay. So read the question. I actually should have hid this drawing because you have to produce the drawing. But, I mean, if you don't know how to produce this, then you're forgetting the whole idea of me working with the student, talking about rope tied to something, yank, and then the thing flies on the diagonal. So two forces, 692 and 423, act on a point. There's the point. The resultant is 786. So you draw it. Ready, set, go! Pumpkin flies through the air. Create the parallelogram so you could use parallelogram properties. Find the angle between the forces that do this action. So I have to find this angle measure. So wouldn't you agree that I could find this and then find this and do what with those two answers? Add them. That's 3 steps. Find one angle, find another angle, and then add them. I have something easier than that. What else could I do that's less steps? That's actually 2 steps, really. And I'm going to leave that hanging out. We finally got it. The students came together. Oh, this is so great. I'm almost about to cry. Okay, so what we could do, not all this, which, do you remember this? Law of cosines, when you were given, you need to find an angle. All right, so we're going to do it. You could find alpha, find theta, and then add them. That's 3 steps. Or we could do this. Okay, here we go, class. More awkwardness. We could find this angle measure. Let's call that angle A, just to give it a name. Okay, here we go. Everyone fill this in. Okay, cosine, hold on, don't say anything yet. Cosine of angle A equals, all right, 3, 2, 1, go. What goes up here? Wah, wah, wah. Okay, you started it? It's not 786, okay? So cosine of A equals 692 squared. Okay, here we go. Plus 423 squared minus 786 squared. Even he's saying something. He stares me down all the time. Over 2 nothing. 692 times 423. Nothing. Okay, so you get A, then you do 180 minus A. Yeah, right? So we found A, and then 180 minus that.
What about the other A? How do you?
Okay, we're missing. Yeah, okay. All right, let's move on. All right, equilibrium. I don't know. Look it up on your own. Okay, this one. Physics people, I don't know if things are different in physics like in math, but I remember back in the day, some students recognize this as a formula. I couldn't care less. You are going to have to make the drawing as well. And the drawing must represent where the simple formula comes from for pulling something up an incline, which in this case is a ramp. Now, a couple questions to get you just to figure this out. One, I don't really have to ask as you draw this. No, just simply draw this as a robot. Watch me. Okay. The steeper the ramp, is it harder or easier to pull something up? Harder. If you got a ramp that's very steep, you're almost getting the full effect of gravity. Okay, and the less steep the ramp, the easier it is to pull something up. And then what if I had my wagon had no wheels and I put sandpaper on the bottom? Would that be easy or hard? Hard. Why? What does that add? A lot of friction. So what's the idea of the wheels? It reduces the friction, and in this case, I think you have to kind of, for this model here, pretend that friction is zero. I don't think any wheel is perfect that actually occurs, but friction is involved. But with a wheel, the friction is reduced to minimal. Let's just say, so it'll be incorporated into this question. So here's what we have to do. Now, I guess I didn't do this first hour real quick, but we should actually, or second hour, should actually look at the question and know that you have to produce a drawing just from this one little sentence. Find the force, Star Wars, required to keep a 50-pound wagon. How is that a force? Well, what is weight? It's the effect of what? And how does gravity affect us in what direction? Straight down. Okay? So gravity is pulling us straight down towards the earth, and we're going to pretend earth is horizontal. From sliding down a ramp inclined, does the ramp incline matter? Yes. The steeper the incline, the harder. The less the incline, the easier. So what you have to understand is from this little from this little word problem, you must present this drawing. So I'm going to explain it. Now this could be any length that you want, but I'm going to do that last. Your first vector you better understand is the weight vector. It is perpendicular to the ground. It is perpendicular to the horizontal. It's actually not perpendicular to the ground. That's completely false. It is perpendicular to the horizontal, no matter what sloped ground you are on Earth. So gravity is affecting us, right to the core of Earth. So it's dragging us down to the core, dead center point. So you must draw that vector. You must draw that vector and give it a length. And maybe relatively speaking, it's hard to do this relative though, compared to what you know your answer is going to be. All right. Now the next thing, what matters? The ramp, right? So this is what we'll call the ramp vector. And the ramp vector is perpendicular to the ramp. That's the whole point. The ramp vector, what the ramp is, matters. The steeper the ramp, the harder it is. So label that ramp vector. Label this weight vector to know how to make this drawing. And then label this. This is the force we're trying to find. I don't know how long it is. We don't know what the answer is. You can make this longer on your paper if you wanted. But this is the force required to hold this at a state of equilibrium. This is to keep the wagon stationary. So what happens if I increase whatever this answer is? Where will this go? Up or down the ramp? Up. What if I decrease whatever I find? Goes down. So we're saying, what is the point where this keeps it stationary? I increase it, I go up. I decrease it, I go down. So what's the state of equilibrium force? Now, watch what I do. This is actually the same idea of a resultant, drawing a parallelogram. You should draw a parallelogram here. Okay, because then what we're going to do with this force to hold this from moving is flash it across to this other side. Now, this kills me. I always teach with the most common mistake. We're going to do two more examples of this. The third one, I'm going to walk around the room and see if you're actually drawing this. And that's your job. You should be able to do this after this because it's really not that hard. But why do I make this 90 degrees here? It's a very simple geometric concept. What is the answer? Why are these both 90? Not corresponding, but you're on the right track of vocab. They're alternate interior angles, so these two angles are equal. I'm going to say this 3 times. The number one mistake in drawing this weights, ramp vector, force vector is putting the angle that's 90 degrees right here, not here. Number one error, 90 here, not here. Number one error, 90 here, not here. Because you're just grasping for something that you just try to remember what good old happy Mr. Samuels told you in class. And you're not using basic geometry. You're not understanding that the ramp vector must be perpendicular to the ramp. You're not understanding that the weight vector is only perpendicular to the horizontal. And then you're not understanding that these are alternate interior angles, so the 90-degree angle must be over here, not over here. That's the problem. Okay, now, how do I get this to be 20 if you can see this? I know this drawing just points an arrow to this. It's very simple. The ramp is a 20-degree ramp. This is 90 degrees. How did I get this to be 70 here? This is all simple geometry. 180 minus, all right, 90 minus 20 also, same thing. And then let's look at this. Do you see this right here? This is what? This is what? 90. What's 90 plus 70? Simple question. 160. What's left over for this little sliver? 20. See, this is a straight angle. So, of course, this has to be 20 in here. So what I'm doing is if a student knew how to make this drawing and forgot all this stuff, it's math 2 geometry. All you need to remember is weight, perpendicular to the ground. Ramp vector matters, it's perpendicular to the ramp. And then you construct your force vector and then do simple geometry after that. Because it's ridiculous how easy this is. How do I find F? Now this is a math 2 question. Sine what? Sine 20 equals what? And why is it sine? Because what side is this? What side is this? Opposite. What side is this? What side is that? Hypotenuse. Opposite and hypotenuse with the right triangle. And then the trigonometry is very simple on this. Very basic. It's all about the drawing. Okay, and then we can get an answer from there. I think it's a made-up person. Okay, so when we zoom in on this, what would the incline have to be to keep this going? So remember, 90 minus this equals theta. 90. These angles are alternate interior angles. So these angles are equal. So that makes this angle have to equal that one in every single case. There is the ramp vectors, or the ramp angle that is equal to that ramp angle. That's how it happens. That's how it works. Weight, perpendicular. Ramp vector, perpendicular to here, so that's a right angle. So I have to find theta. It's sine again. It's actually sine every time on these. What'd you guys get? Should be done. Degrees, right? Okay, now on your own. I'm coming around. Awkward, ugly Mr. Samuelus. See if you can make your own stinking drawing on this question. Emulate. You got to be a better emulator of how this works. Okay, so we got a little ramp. It's only 15. This is 3,000 pounds, so that's 3,000, and it's perpendicular to the ground. There is a ramp vector that you just have to create. And then this has to be parallel. This is the force vector that you're using, however long it is. It has to be parallel to this down here. So you flash that across here. Here's the force that I need. Here's the force that I need there. Alternate interior angles makes it's a right angle. And then like I just said, 15 degrees there, that's 15 degrees there. So it's sine 15 equals F over 3,000. Should not be a problem. There should be no issues with it. All right? No questions. Keep that hand down. All right, here we go. Hey, try this one. And now be your own note maker. And then I want to make sure I get done with this, maybe another bearing, and then help you on a question that we got here. Okay, before I let you, make your own drawing and do it on your own. We got to get this figured out, though. We're making too much of a mockery of this. I don't know if you don't know where north, south, east, and west is on a piece of paper, but everyone's drawing should be relatively the same. So when I see a bearing of 28 degrees, class, answer this question. Is this going in a north or a south direction? Correct, it's north. Is it northeast or northwest? Northeast. You're already telling me you know what a 28 degree bearing is. You remember. That is actually your job. Okay, now, read the question, make your drawing about the things that happen in here, then I'll reveal it. And if you don't get something relatively close to this drawing, you're severely behind. And actually, what's really tough, I was really mean about this, meaning I did create a tough question at the end. But before this, everyone should be able to get this answer. I'm sorry, you should. All right, drawing a line in the sand and telling you what you're responsible for as far as remembering. So number one, we all said this. We all said that we're going in a northeasterly direction because we draw a cross here and the boat starts, ship, leaves on a bearing of 28 degrees means it goes in this direction. And it does do this for 8.2 miles, so we at least have a starting point. Then the ship turns and goes due east. So what kind of line do I have to draw from here? Don't say straight, don't say red. Horizontal. And it only goes 4.3. So you know what? Relative to the question, I just want to make it like that. I don't want to make it longer than that, again, this is where the options are. But this is darn well where your ship better end up. And if your drawing's all cattywampus and doesn't have these points on your pieces of paper where mine are, I will not even look at your drawing. There is something missing that we're not comprehending about these directions that I just can't help you with. Okay, now what we have to do is how far is the ship from the port? Well, now we got some issues. And the issues, quite frankly, are basic geometry. Did anyone find this angle measure? I'm interested. What is it? 118 is correct. I don't know if someone said something different. Here's why. Draw a crosshair on this. What's this angle measure from here to here? 90. Now, how do I find this angle, this little sliver? Alternate interior. This is 28 degrees because this is an alternate interior angle with this one. Geez, that highlighting. A little too large there. Back. So, 28 plus 90 is 118. How do I find x? Not law of sines. This is side, angle, side. Who do you use for side, angle, side? So here we go, everybody. You ready for this fun? X squared equals, come on, ready, set, go. 4.3 squared, come on. Isn't this pathetic, YouTube? Minus 2, 4.3, 8.2, cosine 118. I'll wait for somebody to actually calculate. Does anyone agree with that? 10.9 miles? Yeah. Hey. Oh, are you okay? What is its bearing to the port? That means I changed it. It says from the port, which means what's the bearing from here to here, which was an easier question than this. And I got to be a cowboy and lasso this. Just pay attention. And those that say that this is too hard, you're wrong. Because this is all I have to do. Here's the ship. And all I have to do is draw a bearing on there. That's it. Or draw a crosshair, I mean. And then what's the bearing? How far have I gone right now? Tell me. How far have I gone right now? 180. How far have I gone right now? 270. But then I got to do what with this angle measure? So basically all I need is 270 minus whatever this angle measure is. Let's call this y. Everyone should be able to figure that out. It's not that hard. Okay? So how do I find y now that I got x equals 10.9? The law, anyone? The law of sines. Now that I found 10.9, then I could find y, and then you go ahead and do that on your own. Sine of y over 8.2. And then the bearing is 270 minus that because we're sticking with the same bearing method. Between, what's the matter? 0 and 360. So it's 270 minus whatever that answer is. Something happened funny that I missed. I'm going to end with a question that's actually in your book that is a little bit unique. Okay, two people are carrying a box, and they're carrying it with like a rope situation on it, or so, or these are their arms. But then this is how they figure this out, I guess. Or let's pretend there's ropes tied to it, and this is a shorter person holding it, and this is a taller person holding it. That's their arms, by the way. Hand. Their hands got smashed. I don't know. So, somebody's stronger than someone else. That's fine. Do you know what the resultant is? Like, what's the resultant of the box? Like, what kind of line do I have to draw to really draw the resultant? A vertical. Why? Because what is it? What are we working against? We're working against gravity. So we're pulling this against gravity. So you do have to do number 10. What I just wanted to share was what you got to draw is the vertical, and then maybe flash and make a parallelogram out of that. That is how the box is acting when these two people work on this. So it is a resultant situation where the resultant is vertical because you're working against gravity. Does that make sense? So I just wanted to make sure many times over the years that problem's been a question, or that question's been a problem.